Well, they should just be able to just talk. And it should come out the speaker so you could.
I will just ask.
Yeah. Yeah, it's probably good to say.
All right. I think it's time to start. This is the last session. Thank you, everyone, for being with us right until the end. It's my pleasure to introduce the last speaker of the day, which is William Humans, in this joint work with Jean-François Vias and some other authors, and talking about mildly short vectors in ideal lattices of cyclotomic fields without quantum computers. It's possibly the longest title of all MathCrypt. So, William, the floor is yours.
Thank you. Thank you, everyone, for being here. So my name is William Humans. Like you said, mildly short vectors and ideal lattices of cyclotomic fields without quantum computers. My co-authors are Jean-François Bias, Mohammed Rashad Arukalangara, Klaus Fieker, and Tommy Hoffman. There we go. So that brief outline of this talk, we want to use subfields to find approximate short vectors in ideal lattices. By approximate short vectors, we're referring to something called something that we call a mildly short vector. This is a vector of a lattice, which is within a approximation factor of 2 to the O tilde squared n of the shortest vector of the lattice, sub-exponential approximation factor. If you're familiar with gamma SVP, or the gamma shortest vector problem, this is just a variant of that. And one of the main ingredients that we're going to be using is Bias, Fieker, Hoffman, and Page 2020, normalizations and computational problems in number fields. They present classical methods that allow us to reduce problems in number fields to problems in their subfields. So a brief background on this. So 2016, Kramer, Dukas, Pikert, and Regev showed with a classical computer, there's an efficient reduction of the short principal ideal problem and principal ideals of power of 2 cyclotomics to the principal ideal problem. The short principal ideal problem being just finding a short generator of a principal ideal problem, just finding a generator. And Kramer, Dukas, Wesolowski, in a series of papers show that with a quantum computer, they have an efficient reduction from the search for a mildly short vector in general ideals of these power of 2 cyclotomics to the principal ideal problem. And we'll refer to this reduction as Kramer, Dukas, Wesolowski, CDW. So the CDW approach extended the CDPR approach by introducing the closed principal multiple problem. The idea being that if we have a general ideal that may not be principal, we search for a close ideal that is principal that we can use instead. So the closed principal multiple problem, just a recap, the ideal class group is the multiplicative group of fractional ideals modulo the principal fractional ideals. And it gives us equivalence classes of ideals. So A and B as ideals are equivalent if there is a number field element alpha, such that A equals alpha times B. And we will also be using a minus part of the class group, which is that CLK minus. It's a subgroup of the class group, and it contains ideal classes where the norm of that representative down to from K to K plus being the totally real subfield, is principal. What that means is that the minus part of the class group is the kernel of the relative norm map from K to K plus when acting on ideal classes. So the goal of the closed principal multiple problem, like I said, is given an ideal, we want to find another ideal so that A times B is principal and B is not too much larger, it doesn't grow too fast. So some of the steps in brief, we start by multiplying our input ideal with random small ideals, these A sub 0, until the class of the product is in the minus part of the class group. Then we want to decompose this product in the minus part of the class group according to a set of generators, which generate the minus part of the class group. And so we want, say, a decomposition of alpha prime inverse to look like this. So that the alpha prime inverse is equivalent to the product of these prime ideals to the exponents ti's. when we do this, then we can find a vector V of a particular lattice called the projected Stickelberger lattice that annihilates the minus part of the class group. We won't go into detail on all of that, but if you find a vector close enough to our input vector or exponent vector t, then we can find a solution to this closed principal multiple problem, which is just this ideal we'll define B as A0 times the product of the PIs to the TI minus VIs. And this thing is equivalent in the class group to A inverse, meaning that A times B will be a principal ideal. So since A, B is principal and close to A roughly in norm, a short generator of the product AB will give us a mildly short vector of A itself. So one of the core techniques that we use to do this is going to be norm relations from introduced by Bias, Speaker, and Hoffman Page. So let K be a Galois algebraic number field. If K has a norm relation, then for all invertible elements of K, we have this identity, which is that x to the d is equal to the product of the relative norms down to subfields fixed by hi being subgroups of the Galois group of K, with these exponents ai, bi just being integers and d being greater than 0. And we call d the denominator of the norm relation. We also call these exponents bi and ai the coefficients of the norm relation. So a couple things that are very useful about norm relations is that, well, say we want information about elements of K, or let's just say powers of elements of K, all we have to do is take these relative norms down to these subfields and do what we want there, and then we can recombine this information according to this norm relation, and now we have our information on this power of our element of K. But of course, we don't always want to work with powers or K to the D, so we want to take roots, and that's going to be a theme that we'll see a couple times. And another thing to note too is that this doesn't rule out the case of D being equal to 1, in which case you have the denominator 1 norm relation, and these occur, and they give us a very cheap, basically free way of working in a field by just working directly in subfields. So a special case of norm relations is in the case when we're working with an abelian field. In this case, K has a norm relation if and only if it is not cyclic. And in this case, we actually have an explicit formula to produce the norm relation. So this is just to give you a taste of it, but we basically just enumerate cyclic subgroups of the Galois group to get our subgroups and fixed fields that will be our subfields in the norm relation. And this sort of formula will give us our coefficients of the norm relation. And this is the Mobius mu function in the sum there. And so it's not hard to compute an explicit norm relation given an abelian field especially. And what's very nice about this formula is that it's actually optimal in terms of the denominator of the norm relation, as well as the degree of the subfields that it involves. Because of course we want subfields that have very small degree so that we get the most out of our norm relation. So the degree of these subfields is determined by the largest cyclic factor of the Galois group. And in fact, in the case of a cyclotomic field, the degree of the subfield is bounded by lambda of m, which is the Carmichael lambda function, which just gives the size of the largest cyclic factor. But it's very useful to know that. And some things we can do with norm relations, there are a number of things we can do, but one is recursive computation of S units. So the S unit group, just as a recap, is the multiplicative group of elements, integral elements which have non-trivial valuation only at the primes in the set S. So at any primes at S, it has valuation 0. So if we want to recursively compute this S unit group, we can use a norm relation essentially directly. We can compute S units, the S unit groups of the subfields, and we can recombine them based according to the norm relation, where here, for example, V is given by the subfield S unit groups, and the AIs are the exponents or the coefficients of the norm relation. And this gives us a subgroup of the S-unit group, specifically an index D subgroup of the S-unit group. We want the whole thing, so we need to do another technique, which we refer to as saturation or desaturation. Essentially, saturation is to take elements of V and search for products of them, which give you dth powers. And then we want to take those dth roots and improve the index until we finally get an index 1 subgroup, or the full S-unit group. And a downside of that is, like I mentioned in there, is taking those dth roots. So again, this is normalations. One of the prices you pay is taking roots sometimes. It's generally worth it. But there's also an example from BFHP, their example 5.3. They compute the class group of the cyclotomic field of conductor 6,552, which has degree 1,728. And they're able to compute the class group in 4.2 hours without using S units like we do here. But one of the tricks that they use is to only compute the structure of the class group, so they don't compute generators like we would be doing here. So that is one of the powerful things of normalations, powerful thing you can do if you only are interested in the structure of a class group, for example. So one of the core contributions we have here is ideal decomposition. So in the closed principal multiple algorithm that we introduced or started with, there was an ideal decomposition step that is expensive, and it's one of the reasons that CDW relies on the quantum algorithm for an efficient reduction. And so we want to look at this under the lens of a normalization. And so we take the obvious approach at first, decompose the relative norms themselves in a subfield. So, and we can apply a normalization to ideals just as well as to elements. So we have a relation like this on our ideals of OK. And if we want to decompose A, we can start by looking at this norm relation and decomposing these relative norms individually. And if we do that, we can recover an element alpha and an exponent vector, giving us a decomposition. But like we said, there's that issue of the denominator. So now we have a decomposition of A to the D instead of A. And it's not clear how you can go recover a decomposition of A directly, because alpha may not be a d to the power, the yi's may not be divisible by d, and so we have to do quite a bit of extra work from there. So to start with that, we compute generators of the S-unit group, and as well as a matrix whose rows are the valuations of those generators over the set S. This is a standard practice with computing S-unit groups, and if we do that, then we can solve a particular linear equation. We can find a vector x so that y equals xm mod d. And we use this because we can do some transformations here. So that in the top left, we have our decomposition of A to the D. I'm not going to go through all the steps here, of course, but if we manipulate things enough, we are left with what we see here in the, nope, can't do that, in the very last line, which is we have our alpha prime, and we have a product of delta j's to aj, and then we have the product of the pi's to the d times zi's. So that product of prime ideals we're done with. We've gotten halfway there, because now the exponents are divisible by d. If you want to take dth roots, you can just divide them by d. We're left with this term in the front that we need to figure out something to do with. And just to note that those the delta j's are products of our S-unit generators, so they're actually S-units themselves. And the alpha prime is just a generic element for all intents and purposes. And the AJs are just exponents that we don't know, but we know that they must exist because we know that we should have this decomposition. And just to mention that we are not evaluating these products of elements here that you see. We keep everything in a product representation, the alpha primes and the delta j's, and we'll mention that in a moment why we do that. But with this information, like we said, we have to figure out something to do with those terms at the front, and so we use a technique called taking dth powers modulo S units. So we know that alpha prime is a dth power modulo that set of S units, the delta 1 delta m. either exists these exponents aj that give us this equation. That there should be some aj's so that this product here is a d to the power or some beta. So we can bring saturation back into the picture. Just like when we were computing S-unit groups, we saturated the set V. Here we can just saturate the set U. We just throw alpha prime into the mix, and we really don't have to do anything special, just reuse our saturation tools. And when we do this, we can find those exponents, AJs, such that this thing is a d to the power. So now we have everything looks very nice, and we can take dth roots across the board. And we finally have our decomposition of A over the PIs. So there's a catch here, though, which is that, like we said before, everything was in a product representation. So we can't just take a root. It's more complicated than that. So what we have to do is use a technique called compact representation, where we can sort of manipulate it so that we only have to take a dth root of something that's reasonably small. And so this is an efficient technique, and you'll see it in this field. And so we take advantage of that, and we are able to take the root eventually and recover this decomposition. But some of the applications of this, right away, we can talk about the principal ideal problem. So we can decide whether or not an ideal is principal using decompositions. So the idea is first to take a set S of primes that generates a class group of your field. And we're assuming that we have a normalization, so we can do all this stuff. And we can compute the S-unit group, but we only need to do it once, and we can do this recursively. And then if we want to determine if an ideal is principal, we can just take its decomposition again recursively, like we just showed. And if it has a trivial decomposition, then it's principal. And one thing that I didn't mention earlier on was that we're doing all these things recursively in some fields. This can all be done in parallel. So that's also one of the very powerful things of normalizations. We can do this all separately or in parallel. And then we can also do a search PIP to find a generator for a principal ideal. It's a little bit more involved, and unfortunately it involves computing an S-unit group basically per input. So for each ideal that you want to check, but it is a much smaller S-unit group, much fewer primes in the S-unit group, but it is possible and also can be done recursively. For more applications, getting to the part that we were advertising, we can compute the minus part of the class group. So we kind of mentioned earlier, the minus part of the class group is the kernel of this relative norm map from K to K plus. And so the idea to compute this is if we have a set of generators, S and S prime, for the class groups of K and K plus respectively, then we can decompose the norms of the primes in S over the primes in S prime to get a description of the norm map, the relative norm map. And there's a little bit I'm sweeping under the rug with this, like always, but we can essentially use some linear algebra, compute the kernel of this relative norm map, and we can recover the minus part of the class group. And we can also verify an assumption of the CDW paper. So this is an assumption that the close principal multiple algorithm relies on. And it is the assumption that the minus part of the class group is generated by few ideals of small norm and their conjugates with probability 1/2. So we have all the tools to do this. We can compute the minus part. We can try drawing prime ideals at random that satisfy this and check this probability. And we do that. We have some information on that at the end. And we can also do what we advertised from the beginning, which is compute mildly short vectors, or find mildly short vectors. So it's not too complicated to do that from here. If you recall, the CDW process just use the close principal multiple technique, as well as the existing techniques for finding a short generator of a principal ideal. So we can take this close principal multiple algorithm and that decomposition step that was expensive and required a quantum algorithm in order to be efficient. We can use our normalization variant that does this recursive decomposition instead. And so as far as the complexity goes, everything is determined by the subfields. So up to polynomial factors, the search for mildly short vectors is totally determined by the subfield S unit group and ideal decomposition costs. If you remember when I mentioned the lambda function earlier, this is the size of the degree of the largest subfield in the normalization. In the case that lambda of m, so that degree, is less than the degree of the field itself to the a, where a is less than 3/4, we have a super polynomial improvement over the BKZ algorithm, which finds a mildly short vector in time 2 to the O tilde square root n. And the BKZ algorithm is in general ideals, general lattices, the state of the art for finding, if you wanted to find a mildly short vector. So we can outperform BKZ in these cases. And we also show an infinite family of fields where the cost is in fact this, I won't say out loud, but it is essentially this complexity, 2 to the n to the little o 1 in this particular family of fields. And I just want to emphasize, though, that this is a very narrow range of fields that satisfy this, but we do get a very big improvement over BKZ asymptotically in this family. And so this is a bit more information on the how often you can expect to find fields that where you can get this sort of improvement. So the rightmost column there is the probability of finding a field where we have that the degree of the largest subfield is less than the degree of the fields at 3/4, where, like we said, we have a super polynomial improvement over BKZ. Up to 1,000, for example, 30% of fields emit a normalization that allows us to do this. And that's how you can continue to read this. As you try to restrict the degree of the subfields more and more and get them to be smaller and smaller, you can see that the probability of finding a normalization or field that has such a normalization gets very small. And I briefly mentioned that we can work on, or we can verify this assumption or compute some evidence for this assumption from CDW about the minus part of the class group being generated by very few prime ideals of small norm. And so we did run some experiments on this because just about everything we talked about here is implemented. And this is the results of some experiments. We were able to do, for example, the first line, sample D, 3 ideals at random of norm less than B, had probability of 87% of generating the minus part of the class group over 100 iterations. There we go, and that's it.
Thank you, William. If you have a question for William, please use the microphone. Come up in the microphone. Yes.
Yeah, I might have a question. So if I understood it correctly, you dequantize the Kramer and the Dukas and Wesolowski algorithm by replacing the quantum part by some classical part. So now it's fully classical. Yeah.
Yes, it's not, we don't get the same efficient reduction that we would have with the quantum algorithm, but we get something which, like in that very narrow family of fields that we showed, is very close to being polynomial, but not as efficient though.
Okay, so yeah, okay, that was I was wondering. So it's on the trade-off of only being efficient on very specific fields.
Right, and still not reaching a polynomial complexity for that reduction.
Okay, thanks for clarifying.
Sure.
We have more questions, or perhaps questions from Zoom. You can directly unmute yourselves. Looks like there's no more questions, so please let's thank William again.